So which one of the following statements best explain why tiny bits of paper are attracted to a charged rubber head? So that's for number 5. The answer is letter C. The paper becomes polarized by induction. Again, what we mean by this is that, again, if we assume that the rod is negatively charged, it will create an electric field on its surroundings. Thus, the paper, these pieces of paper near to it will get polarized. That means the orientation of its electrons will change because of the presence of the electric field created by this negative charge rod. Or more specifically, the paper becomes polarized by induction. That means the electron changes its orientation without having them in contact with this negatively charged rod. So again, the electrons will tend to move on this side, or it will tend to move away from this negatively charged rod. Thus, the thus the region of the paper that's near to the charged rubber rod will tend to move away from it, thus leaving this region net positive charge and this region net negative charge. So that's the reason why these pieces of paper will tend to attract to this charged rubber rod. So the answer for number 5 is letter C. Okay, so for the problem solving, number 1, an unstrained horizontal spring has a length of 0.32 meter and spring constant of 220 newtons per meter. 2 small charged objects are attached to this spring, one at each end. The charges on the objects have equal magnitudes. Because of these charges, the spring stretches by 0.02 meter relative to its unstrained length. Determine the possible algebraic signs and the magnitude of the charges. So again, for the possible algebraic signs, again, since the spring stretches or its length increase, so again, this is the figure before we attach the charge spheres or charge objects, and this is after we attach the charge objects. So we have an increase in length, a positive increase in length, or a positive increase in length, or a positive change in length. We have 0.02 meter increase of its length, and this is also the value of its spring constant, 220 newtons per meter. So since the spring stretches or its length increase, charged objects must have repelled each other. Thus, the sign of the charge of each object must be the same because like charges repel. So it could be either both positive or negative. So that's the possible algebraic signs. It could be both positive or negative. Okay. For B, the magnitude of the charges. So again, after you attach this charged object on the spring, again, the result is that the spring stretches from its unstrained length. So if you're going to consider only this charged object and look at the forces that is acting on it, we have this one. So if we assume that the charged object is positively charged, so we have these 2 forces that is present on this positively charged object. So here we have this F charge. This is the force that is created by this charge. Again, since they have the same charges, the same sign of charges, the forces is to move it away from this one. So that is why the direction of F charge is away from this object, because again, they tend to repel. And also because this charged object here is attached to the spring, and again, it's in equilibrium position, there is also a force that is due to this spring with equal magnitude of this charge. So the force that is created by the charge to this positively charged object is the same magnitude of force created by the spring on this charged object, because again, this system is in equilibrium. So therefore, F charge is equal to F spring. Again, F charge, that is the force created by a charge, is just given by the Coulomb's law. So we have here 1 over 4 pi E sub O, Q1, Q2 over R squared. And F spring, we have Kx. So again, since Q1, Q2, these are the magnitude of the charges, since they have the same magnitude, right? Since they have the same magnitude of charge, again, it's indicated here. The charges on the objects have equal magnitudes, and also they have the same sign. So again, even if it's both negative, it will have this, if we multiply both Q1, Q2, if we assume they are both negative, it will result to a positive sign, right? Negative times negative, positive. So we have this Q squared, right? So if we assume Q1 and Q2 is equal to Q, or Q1 and Q2 is equal to negative Q, if we multiply both Q1 and Q2, it will always result to Q squared. So we have 1 over 4 pi E sub O, Q squared over R squared, and that is equal to Kx. So again, if we try to solve for Q here, if we rearrange this equation, we have Q squared is equal to 4 pi E sub O R squared Kx. And if we take the square root on both sides, we have this Q is equal to plus minus square root of 4 pi E sub O R squared Kx. So now the next step is to substitute all the values. Again, we know that 1 over 4 pi E sub O is approximately equal to 9 times 10 to the 9. Thus, 4 pi E sub O is just 1 over 9 times 10 to the 9. And R squared, it's given. It's the distance between the charged objects. So that's 0.34. So we have 0.34 squared. K is the spring constant, 220. And X is the change of its length from its unstrained length. So it's the amount of change from its unstrained length. So we have 0.02. So if we solve this one, what we will get is plus minus 7.517 times 10 to the negative 6 coulombs. So that's the magnitude of the charge. So again, it could be both positive or both negative. So that's why we have this plus minus sign, because again, it has these two possibilities. It could be both positive or both negative. The answer is 7.517 times 10 to the negative 6 coulombs.